introduction. So we are going to begin a new chapter. So after chapter 15 and 16, we introduced the electric force, electric field, and now we're going to introduce the current and resistance. So when we have an electric field, say in a conductor, it can make the electrons move in the conductor. So that constitute what is called current. Current is nothing but the motion of charges. Okay, that is what current is. Good morning. So let's see what we have in the content for this chapter. We have got 8 sections. The last section we will omit, the electrical activity part. Okay, so section 1 or the topic 1 is electric current. So we'll introduce what is an electric current. So we just say current. So when you say current, we mean electric current. There can be water current as well. Okay. Then we will look at the microscopic view of this current, and we relate the current to what is called the drift speed of the charge carriers in a conductor, meaning like electrons or the ions. Then topic 3 or section 3, measuring current and voltage in a circuit. Voltage is the potential difference, what we learned before. So in electric circuit, we mentioned, we call it voltage, not potential difference. Section 4, we will introduce the new concept called resistance and resistivity, which is related to the resistance, and Ohm's law, which is about resistance. Okay, how the resistance varies with the voltage. That is to do with the Ohm's law. Then section 5, we will look at how the resistance varies with temperature, then electric energy and power, and a little bit about superconductors. There's a class of conductors which is superconductive. Okay, we probably heard about superconductors. We'll briefly describe these superconductors in the last section. Okay, right. Let's begin with the current. Are you guys all listening to me? Are you there, or you just logged in and doing something?
Doctor. Yes, doctor.
Okay, thank you very much. Current. Okay, now you should start beginning the subject. Okay, only when you like a subject, it is easy to learn it. Otherwise, it becomes difficult. Okay, so just keep an open attitude. Okay, all things that you learn, any new thing, you should take it as interesting. Okay, challenging. So current, electric current. Okay, that's what we mean when we say current. Initially, practical applications were based on static electricity. Like static electricity means a charge that is not flowing. Okay, we can charge an object heavily. So there are initial applications. In the beginning, we are talking about the history. The practical applications were based on static electricity, but the moving electricity or moving charges, it came later. The battery or a device which can drive the current around in a conductor, battery like the cell in your mobile or in your flashlight. The voltaic cell was invented in 1800 by an Italian physicist, Alessandro Volta. So that's why the name is volt for the potential difference. Okay, the unit for measuring after this guy, Alessandro Volta. Steady source of electric current. Now we are introducing, okay, we didn't come to any equation formulas yet. We are talking about how the current come into being. Initially, we didn't have moving charges. Then after the invention of the battery, we were able to make the charges move in a circuit. That started the electricity revolution. Steady source of electric current allowed scientists to learn how to control the flow of electric charges in circuits. Now let's define this electric current. What is an electric current? The current is the rate at which the charge flows through a surface. So that's how we define the electric current. We use the symbol I, okay, the big I for electric current. And the definition is how fast charges flow through a given surface. Okay, we have we look at a surface, and through that surface we time how many charges are flowing per second. That will be the electric current per unit time. So look at the charges flowing perpendicularly through a surface area of A. Then we say the average current is equal to the amount of charge that flows perpendicular to that surface divided by the time it takes. So you can see the unit for electric current going to be Coulomb, because charges are measured in Coulomb, and the time SI unit. The time is measured in second, so it is Coulomb per second. But as always, we don't want to say too many units, so we're going to call this ampere. That's right. Again, after a certain scientist who worked on this electricity, after ampere, his name is Ampere. So after that scientist, we call it ampere, and the symbol is A. So the SI unit for current is Coulomb per second, but we have a single name for Coulomb per second, which is amperes. So 1 ampere is 1 Coulomb per second. All right. Now, that was the average current, right? So the definition of average current, we look through a surface and the charges flowing perpendicular to that surface for a time of delta t. This is the average current. But like we had in mechanics, we go from average to instantaneous. So the instantaneous current is at one particular moment, not over duration of time, is defined as the limit of the average current as the time interval goes to 0. If there is a steady current, okay, suppose the current is constant, okay, steady, the same value, we have the same rate, steady current of current flowing, then there is no difference between average and instantaneous. It's like the velocity. So if the velocity is constant, for example, then there is no difference between during that period of time where the velocity is constant. Instantaneous velocity at each point is the same as the average velocity for the duration. Similarly, when you have a steady current, the average and instantaneous currents will be the same. SI unit for instantaneous current is the same as the SI unit for average current, amperes. Okay. Right. So we're going to continue to look at this electric current. The direction of the electric current. So here this figure, look at this figure, we are showing an area A, and we are watching the charges flowing, crossing this area A. Then we know the current is defined as how much charges flow perpendicular to that surface area per given amount of time. That is the current. Now, the direction of the current is the direction positive charges would flow. Okay. So because it doesn't matter whether the charge is positive or negative, we have a current. So, okay, whenever there is a positive charge flow, there is a current. Whenever there is a negative charge flow, also there is current. So the direction is defined by the direction of the positive charges flowing. So if I look at the figure A, so we will say that the direction of the current is to the right, because the positive charges are flowing to the right. So the direction of the current is to the right. Now you should pay attention. Okay, so for whatever I said is easy things, but here probably, maybe you should understand it better. So pay 100% attention, please. Okay, right. This is called the conventional current direction. Okay, that is how we, because let's look at the B. Now, what happens now? Negative charges are flowing to the left. Let's say, let's say some negative charges are flowing to the left. What is the direction of the current? It is not the same direction as the negative charges flowing, but in the opposite direction to the negative charges flowing. So the direction of the current in B also will be to the right. Okay, is this clear to everyone? You get the convention. Convention mean agreed upon. So we agree upon, okay, the scientists get together. So they put the convention standard. Okay, this is how we are going to treat the direction. The direction of the positive charges flowing is the direction of the current. For a negative charges flowing, the direction will be opposite to the motion of charges. Okay, so it is like saying the negative charges flowing left is equivalent to the same amount of positive charges flowing to the right. Is this clear to everyone?
Yes, it's clear, doctor.
Okay, very good. So we got another thing that we define. It is a common practice to refer the moving charges, because in a conductor, like let's say a metallic wire, like a copper wire, that's what we normally use in electrical circuit. It's a conductor. Copper is a conductor. When you apply an electric field via a battery or something, the current will flow because of charges moving through the conductor. Now, I have a question for you. Is it the positive charge as it is flowing through the copper wire? So let me draw the copper wire. Oops. What happened? Okay, here. Let me draw a copper wire. So this is copper wire. And say there is a current flowing to the right. Now, what is the charge that is flowing through this copper wire? Is it a positive charge which is flowing, or the negative charge it is flowing? This is a question for you. Abdullah? Amina?
Doctor, the question is...
So say we have a wire. Okay, and we know there is a current there in this wire. Say there is a current flowing. Now, what is the thing that is flowing? Is it a positive charge is flowing or a negative charge flowing in the wire?
Positive.
Okay, you mean the protons are moving? Positive charges are
no,
protons.
Electrons are moving.
Electrons are moving because protons.
And electron is negative, right?
So the answer is negative charges that are flowing.
Ah, okay, I understand now.
Okay, so the charge carrier is the electron. In a metallic conductor like a copper wire, the charge carrier, whenever there is a current flowing, what is the charge carrier? Is the electron. Okay, so because protons are fixed to the atom nucleus, it cannot, they are not free to move. Only the free electrons, the metals have free electrons. These electrons that are moving through the metallic wire. So we refer to the moving charges as the mobile charge carrier. You know the meaning of mobile. Okay, mobile means moving. Okay, good. A charge carrier can be positive, okay, but in a metallic wire, conducting normal wire, the charge carriers are the negative charge, the electrons, okay, namely the electrons. But can you have positive charges as carriers? Yes, not the protons. In a liquid solution like a sodium chloride solution, the ions, positive ions can move. That constitute as a that is possible. Okay, it is the whole ion, which is not the proton itself. Say positively charged sodium ion, for example, can move towards the positive anode, or the positive cathode is the negative. Yeah, I can't remember exactly. Okay, well, it can move to the positive terminal of the in a solution. Okay, so it is possible for we to have positive charge carriers, but in a wires, in a metallic conductors, the charge carriers are electrons. Okay, so now a little bit of power here. In a conductor carrying current, the electric potential of the charge is continuously decreasing. So what happens when there is an electric current? We have got, as these charges moving, the potential of the charges is continuously decreasing. Always the charges will move such that the potential energy is decreasing. That was another question in your exam, which we have discussed in the previous chapter. Positive charges move from high potential to regions of low potential. Now it's about potential, not potential energy. Okay. Negative charges move from low potential to high potential, but both of them are moving such that the potential energy is decreasing. So the change in the potential energy is Q into delta V. Suppose it is a positive charges, this will be negative because positive charges move from high potential to low potential. Potential energy V I'm talking about. So delta V will be negative, Q is positive, so we get the change in the potential energy is negative. That means the potential energy is decreasing. So suppose the charge carriers are negative, suppose, not electrons, say positive charges, then Q is negative, delta V is positive because negative charges will move from low potential to high potential. Then again, we get the change in the potential energy to be negative. So it doesn't matter whether you have positive charges or negative charges. The end result is the charges move such that the potential energy decreases as they move. The power delivered to the circuit element is the energy divided by the elapsed time. So what happens in a circuit? The potential energy is delivered to the circuit. Okay, that is why the potential energy is decreasing as the charges move, and the amount of the power is the amount of energy divided by how much time it is taken to deliver that energy. So that is power. We have defined power in mechanics as energy divided by time. It is the same concept here. The power is how fast the energy is being delivered. So that is power. We'll come back to the power later at the end of the chapter. Okay, now let's go into the atomic level, where in a microscopic level, to see the connection between the flow of the movement of the charges and the current. So the drift speed of the charge carrier, the electrons, will take the conductor and the current. Whether we can relate the drift speed of the electron in a conductor to the current. So to do that, we are looking at a cross-section of a wire here, a conducting wire. And here we show an area. And through this area, let's say the area is A, we are looking at charges flowing. Well, the charges are actually the electrons, but it doesn't matter. We can assume the flow of electron to the left is equivalent to flow of positive charges to the right. Okay, so when a current flow to the when electron flows to the left, we can consider it to be equal to the positive charges flowing to the right. So charge particle moves through a conductor of cross-sectional area A, and let's say the number of charges or charge carriers in this conductor per unit volume is n. So n is the number of charge carriers per unit volume. So that is the density of charge carriers in this conductor. So, density we give like per unit volume. How many charge carriers per unit volume? Let me say it is equal to n. Then, if we wait an amount of delta t, during that period, this charge carrier will move a distance of Vd delta t. Let's say it is delta x. That delta x will be equal to Vd delta t, where Vd is the speed of these charge carriers, speed of these charge carriers. What is the definition of speed? Suppose there's a constant speed, it will be the average
distance
speed.
over.
Yes, the average speed is equal to distance divided by time. So the Vd is equal to distance divided by time. So I can say delta x is equal to speed, average speed multiplied by the time taken. So in that period of time, let's say if it is moving at delta x, a distance of delta x, and it can be given as the drift speed multiplied by delta t. We call it drift speed. The reason we call it drift speed is, the charge is going to move in all, not necessarily in the same direction, but in all direction, but on average it is going to move in the direction of the current. So that is the drift speed. Okay, now if we take the volume of this from in an interval of time delta t, how much it has moved, the volume will be area multiplied by delta x. For delta x, I can write v d delta t. So this is the volume of this region, and if I multiply by the charge density, the charge carriers density n, this will give you the total number of charge carriers, because n is the charge carriers per unit volume, multiply by the volume that we have, which is a Vd delta t. This will give me the total number of charge carriers. Let me call it delta Q. So this is the amount of charge in this volume. Let me go to the next slide. So this is 30, I told you there. Now how we got this. So we say that A delta X is the volume. So A delta X is the volume multiplied by the charge carrier density. This will be the total number of charges. Then you multiply by Q. Q is the charge of a charge carrier. Let's say these charge carriers have a charge Q. So total number of charges multiplied by the charge of one charge carrier will give us the charge. So I shouldn't have written this delta Q here. Now what we have here is the total number of charge carriers. Then you multiply the total number of charge carriers by charge of one charge carrier. That will give me the charges in that volume. So now let me divide both sides by delta t, this equation, delta t on this side and delta t on this side. And this is the speed, which we call the drift speed. And this is what? This is our definition of the current. Delta Q over delta T is the current. So what we finally get is this equation. I is delta Q over delta T, and then Q, this is Vd, and that is A. So now we got a relationship between the current and the drift speed. And this is the area of the cross section, and n is the density of charges, how many charges per unit volume, and Q is the charge of one charge carrier. Okay, fine. So we got one equation, the first equation of this chapter, which relates the current with the drift speed of the charge carrier and the area and the charge of a charge carrier, and the charge density. Okay. So if the conductor is isolated, the electrons undergo random motion, but when you apply an electric field in the conductor, it makes the charges to move in the direction of the electric field. Well, if it is positive charges, if it is negative charges, it will move in the opposite direction of the electric field. Because, you know, the force on a charge in an electric field is given by this equation. That's the definition of the electric field. So if Q is positive, the force on the charge will be in the same direction of the electric field. If Q is negative, the force on the charge will be in the opposite direction to the electric field. So now let's look at what happens in a conductor. In a conductor, the charge carriers are electrons. So we are taking an electron here. Let's say we have applied an electric field to the left by connecting it to a battery. That is how we get the electric field in a conductor. Then if the electric field is not there, the electrons will be moving in all directions randomly. So there is no net motion. Okay, if one electron is moving to the right and there'll be equal number of electrons going to the left, and there is equilibrium in the conducting wire, there is no net motion of the charges. But the moment you apply an electric field, say to the left, the electron will be feeling a force to the right, because the electron is a positive, electron is a negative charge. So the force on the electron will be to the right. So although it still seems like the electrons are, you know, randomly moving, but on average, there is a motion to the right. Why this zigzag motion? Because electrons will feel a force to the right, because there is electric force to the right. But as it moves, it is going to collide with the other electrons, the other nucleus of the atom. Okay, the atom itself, the crystals in the conductor. So there will be a lot of collisions occurring. But however, it will manage to move to the right because there is a force given by the electric field in this conducting wire. So although it seems to be randomly, you know, colliding in all direction, but there is an average motion to the right. So that's why this drift speed of these charge carriers are small, because of all this collision and deflection, although it is trying to move to the right because of the electric force. This drift speed is small. Okay, small, I mean, it is not a very big value. We can calculate the value, it will be like some centimeters per second. But we will come back to this. You know, we'll compare this drift speed to the actual speed of the electric field. The sharp changes in the directions of this electron, although it is trying to move to the right because of the electric force, it has been, every time it is collided, it is being given velocity to the left sometimes. So that's why, you know, the drift speed, the average speed decreases, is small. But however, there will be a net motion of these electrons in the opposite direction to the electric field, because the electric force is in the opposite direction to the electric field, it being a negative charge. Right. Now, I have here a link from this website. I'm going to go to that website and to show you how simulation of how the electrons move when you set up an electric field in a conducting wire. Okay, let me open that. I have already opened that link. When you click on that link, you will come to this. And people, please, I mean, I don't have anybody here physically in the classroom. Okay, we are all sitting there at home. So you can also click on that link. Okay, it is better that you also do it like a lab. Okay, this is kind of a lab. You know, you can really construct the electric circuit and play with that, and you can see what is happening when you turn on the switch and you connect a battery to electric circuit and how the electrons are moving and so on. It's very nice. So are you doing it with me, please? Yeah, okay, that is it, yeah.
Yes.
Please, yeah, okay. Please click on it, and Amina has put it in the chat. You can click on that link as well. Okay, you don't have to open this course website. Thank you, Amina. Is it for everyone? Everyone? No, you said privately. Okay, can you put it everyone? So, copy. We can see. Okay, then fine. If you can see, fine. We can. Yeah, because Amina. Okay, fine. Let me. You can open the slide, but anyway, let me see if I can copy and paste it. Just give me a second, please. Copy hyperlink. Now I will give it to everyone in the meeting. Oops, why is it not coming? Paste. Okay, can you guys see me in the chat box now? You can click on that and then you will come to this page. It is good we do it together. Then when you come to this, click on this play button, not the download, the play button. Then you will get this. Okay, it's taking time to load. Let's see. Waiting, still waiting. Why? All right, there it is. We are ready. So please, you also do it in your own laptop. Okay, click on the intro. Okay, right now we're going to make a circuit. So I'm going to choose a wire and bring it, drag it there. It's a wire, a piece of copper wire, a metallic conductor. And then take a battery. Okay, I'll take a switch as well. Okay, just drag and drop. I'll take another wire and connect the switch to the wire. Okay, I'm going to make it vertical, this guy. Get some more wires. Is this a wire or a resistor? Okay, I think I took a resistor, not a wire. This is a wire. Okay, take another wire. Okay, I don't. Okay, right, fine. I can drag the one wire. I don't need extra wires. Okay, right. So let me take another wire because I want to make it go like that, and take a bulb. The bulb has two end, right? One positive end, just two end, this end and that end. So I'm going to take another wire and go and make it a circuit. Okay, so we got a circuit now. It's very nice. Okay, you can have a feeling of constructing an electric circuit. Okay, there it is. We got an electric circuit. It's fun, yeah. Okay, right now it's a very simple circuit. We got a battery and a bulb. So you know, if you connect a battery to a bulb, the bulb will light up. That's because the electrons charges flow, we have electric current. What is an electric current? Flowing of the charges. So when the charges flow through this bulb, electric current through the bulb, through that tungsten filament inside the bulb, which is under vacuum and so on, so it doesn't burn. It will get very hot, red hot and white hot. So that's why we get the light energy coming out. So let's do it. Oops. Okay, just click on it. Okay, just click on it, it switch closes. Click on it again, the switch open. So let me do it again. Now click on the switch, the bulb lights up, and click it again, the switch open. When the circuit is open, the current cannot flow, then we don't get the lights on. So that's what happened when you press the switch. Okay, now I have a question. Yes, India, it's nice. Now the question is, when I turn the switch on, the bulb lights up immediately. There is no time at all. It looks like very fast, instantaneous, like the speed of light. The speed of light or the speed of electromagnetic waves is 3 × 10⁸. It is like 300 million meters per second. Okay, that is the fastest speed you can. It really, there is no time gap between closing the switch and the light coming on, because it happens in the speed of light. Okay, the speed of electromagnetic wave. My earphone got burned. I don't know why. Probably you shorted it. Okay, anyway. Okay, now my question is, let me open it. The drift speed of the electron is very small, right? It is like some centimeters per second or even less than that. And I can't remember exactly. But if that is the case, you need the electron from the battery. This particular electron, okay, I have now shown, to come all the way to the bulb and then flow back to the battery, then it will take a long time. We will not have the bulb lighting up instantly like we are seeing now. By looking at the simulation now, you should know the answer, because when you close the switch, you don't need to wait for this particular electron to come to that bulb. Okay, this particular electron, you don't have to wait this particular electron, okay, to go flow through the bulb and come back for the light to light up. What happened the moment you close the switch, the electric field will be instantly everywhere. Well, not instantly, at the speed of electromagnetic wave, okay, electric wave, will be felt at the bulb. So the electron already in the bulb will start moving. So the speed is what? The speed that is relevant here, not the drift speed of the electron, but rather the electromagnetic wave, speed of the electromagnetic wave, the electric field. The moment you close the switch, the electric field from the battery will travel at the speed of light. It will be felt at this electron already inside the bulb at the speed of the electromagnetic wave, which is the speed of light. I hope I got this across. I mean, did you understand what I'm trying to convey to you? Amina?
Yes.
Very good. Okay, thank you. See, now I'm going back to the slide. The electrons already in the bulb move in response to the electric field set up in the complete circuit. You don't have to wait the electron near the battery to make the journey around the circuit to make the bulb light up. So that is a trick. Okay, the battery in the circuit supplies energy, not charges. The battery supplies the energy. It doesn't have to supply the charges that is there and have to take all the way around. It supplies the energy. The electromagnetic field is felt at the bulb itself, and those electrons already in the bulb will start moving, that create the current. The drift speed is actually much smaller than the average speed between the collision. When a circuit is completed, the electric field travels the speed with the speed close to the speed of light, although the drift speed is on the order. See, this is the speed. Okay, now it is less than centimeter. Centimeter is in the -2, right? It's in the less than even millimeter. 1/10 of a millimeter per second. That is the speed of its drift speed of the electron. Very small speed, but it is much smaller than the the, the electric field, the electromagnetic wave, the light speed. Light is an electromagnetic wave, right? You know that. Okay, circuits. Now we go into circuits. Michelle asking me, wow, that we can measure the current. Yes, yeah. We will go back to this website, okay, to do have more fun. But you know, this is the first step. Okay, so I just demonstrated to you why when you close the switch, the bulb lights up almost instantly, although the drift speed of the electron is very small. Okay, now we'll go back to this website again to demonstrate more things later. Okay, Mashal, we can measure the current and so on. Circuit. The circuit is a closed path of some sort around which a current circulates. You know what is the meaning of circle? Circle, you know, coming back to the same point, right? Go round and come circle round. So circuit is a closed path, like we had before with the switch. When you close the switch, it's a closed path of some sort. It doesn't have to be exactly a circle. It can be any sort in which the current can circulate, okay, go round. A circuit diagram can be used to represent the circuit. Okay, circuit diagram. A diagram consists of, you know, the wire is represented by line and the battery is represented by certain symbol and so on. Quantities of interest are generally current and potential difference. So in a circuit, the quantity that we are interested in are these two, current and voltage. Voltage is the potential difference, right? Another name for potential difference that in electrical engineering, they use voltage, okay? The potential difference, yes, they use it, but commonly the voltage. Voltage means potential difference. Right, here we are. Now, let's go back to the website. I have some more fun. So here, we are going to construct the same circuit in the website there. So let's see what is there. We have a battery. Okay, the battery has negative, positive terminal, and it is connected, the yellow, okay, this is the circuit. This is the circuit, the bulb. This is the circuit, okay, it's a circuit. Then we have got some devices. This is voltmeter.
Voltmeter and ammeter.
This is ammeter. See, voltmeter, meter mean measuring, right? So voltmeter mean measure volt. Ampere meter. So you don't say ampere meter, you say ammeter. Ampere is the unit for measuring the current. So ampere measuring. So the current measuring. So that is the name. Ammeter measures the current. Voltmeter measures the voltage. So we are going to set up this circuit and we will measure, and then we will learn some more while we are at that website. So let me go to the website again. Right. So we have the circuit already set up with the switch. Now we want to measure. Okay, I don't have a voltmeter. Where? Oh, there is no. Okay, maybe I should use the other one. Okay, let me go to that. There are two. I'm going to take time again. Maybe I should have downloaded the. Why is it taking long? Okay, right. I should do the lab, okay, not the introduction. So click on the lab. This probably has still maybe it is. Oh, it's here. I'm sorry. Okay, because the chat box is hiding it. That's why I didn't see it. Okay, right. Okay, fine. So we are going to set up the circuit again. No problem. Are you guys with me?
Yes, doctor. Yes, doctor.
Yeah. Okay. All right. I'm just it's right. So we got a wire, a battery. Okay, maybe a bulb as well. More wires to get it go like that, and more wires. Better have the switch, okay, because switch is an important part of a circuit. Okay, we can have it closed. We don't want to drain the battery to having it closed all the time. So keep the switch. Okay, and one more wire to complete the circuit. Okay, you should put it. See, you should not put it here. That will, that will short the circuit. It will bypass the bulb. Okay, right. Okay, so we have the circuit and with the switch. Now, I want to measure the voltage. So I need a voltmeter. Take the voltmeter. This is the voltage meter, voltmeter, and this is the ammeter. Okay, there is another kind of ammeter, but we'll use this ammeter. Okay, this conventional standard type. Right now, what we need to do now to find the current through this circuit, current through this bulb. I want to know what is the current that flowing through the bulb. Then I need to connect this ammeter in series with the bulb. Okay, but
And the voltmeter
we
and purple.
yeah, whatever the current that flows through the bulb has to flow through the ammeter, right? So that means it is a series connection. I hope you understand. We talked about in respect to the capacitors in series and capacitors in parallel. So when you connect two capacitors in series, you connect N to N, right? So the charges that flows through one capacitor will flow through the other capacitor. It has the same charge. So likewise, if you want to measure the current through this bulb, the same current should flow through the ammeter as well. So it should be connected in series. So let me cut this and then connect it to this and then take another wire maybe better. See, now you agree with me? Oh, let me open the switch. Where is the switch? Okay. I like to have it a little bit down. So let me get another wire. Right. See, now my point here is an important point. Okay. So please don't neglect what I am saying now. If you want to measure the current through, say, this bulb, you have to connect your ammeter in series with the bulb. Okay. That is how it is done. So this is something important here. Then I want to measure the voltage. How do I drag it?
And parallel.
Sorry. Why can't I move it? Okay. Okay. Never mind. So I want to move the whole thing. Okay. So voltmeter has to connect it in parallel. I want to know what is the potential difference or the voltage across the bulb. Okay. So I need to connect one end of the voltmeter to one end of the bulb and the other end to the other end of the bulb. Okay, right. So now it is reading 0. Why? Because the switch is not closed.
Not close, yeah.
Yeah. So let me measure the voltage across the battery, okay? Even if it is not closed, it doesn't matter. We can measure the voltage. See, 9 volt, because we took a battery which is 9 volt. There is no current flow, but there is a potential difference between the ends of the wire. So that is what is being measured. Now, if you close this, will the voltage of the battery change? No. That's because we'll come to that later, okay? Because there is no internal resistance to the battery, so it will be the same voltage that is appearing. I want to measure the voltage. Now, let me go back to this slide. Okay, the battery is measuring, the voltmeter is measuring the voltage across the bulb, right? So let's do the same thing. Turn the switch on. Okay, it is 9 volt. Okay, now there is no voltage, you touch it, it's a 9 volt. Because all the voltage that is from the battery is appear across the bulb, because it's not dropped through anything else. Maybe let me add a resistance. No, in this slide there is no resistance. Okay, so we just showed. Okay, what about the current? Oh, we didn't look at the current. Current is 0.9 amperes. So when the voltage is 9, the current through the bulb is 0.9 ampere. The potential difference across the bulb is 9 volt and the current is 0.9 amperes. Okay, nice. Okay, right. We will leave it like that. Maybe turn the switch off so it doesn't reduce our battery. Okay, so we are not wasting energy. Okay, I know I'm joking. So let's go to the slide. Okay, presentation mode. Right, let's move to the next slide. Yeah, it is basically the same thing. See, this is our circuit, but this is a kind of a real thing. But let me draw it as a circuit diagram. So you replace the battery by the symbol. The battery symbol is 2 lines, short line for the negative end, positive end of the, sorry, negative end of the battery, and the big line for the positive end of the battery. And the bulb is shown like this symbol, okay, like that. And the ammeter is with the circle and A inside. A stands for ammeter, and the voltmeter is V inside it. Okay. Now, the voltmeter has positive, negative. Okay. Even the ammeter has positive, negative. So I should have told you about that when I was showing the simulation. So you connect the positive end to the positive side of the battery and the negative end the other side. So it will show a positive value in the voltmeter. And if you connect the correct positive side of the battery from the ammeter and the negative side, the current will be shown as a positive value. Otherwise, it will show a negative value. It doesn't matter, so you know why it is doing that. Okay, so what is important to realize here? The way you connect these two instruments. Ammeter is connected in series with the element through which you want to measure the current, and the voltmeter is connected in parallel across the element through which you want to measure the voltage or the potential difference. So what you want to know is the potential difference between these 2 points. Let me call it AB. So you want to know what is the potential difference VAB. That to do that, you have to connect your voltmeter, one end of the voltmeter touching point A, the other end touching point B. So it is connected in parallel. Hope it makes sense, Mashal. You want to say something? Okay, let's move on. Ohm, that's the name of a person, a scientist. He's the one who formulated the concept of resistance. What is the meaning of resistance? Resistance is the resistance to the flow of charges through a conductor, okay, or anything, not necessarily a conductor. So that is done by, he formulated this concept of resistance. He discovered that there is a proportionality between the current and voltage, meaning when you increase the voltage, the current increases. When you decrease the voltage, okay, the potential difference you apply through 2 points A and B, that is the voltage or the potential difference. For a large potential difference or large voltage, you get a large current. If you decrease the voltage, you get a smaller current. So he's the one who discovered this, and he introduced this concept called resistance. How? Let's see. In a conductor, the voltage across, a voltage applied across the ends of the conductor is proportional to the current through the conductor. The constant of proportionality is called the resistance. Oops. We use the symbol R, so we say R is equal to the potential difference divided by the current. Okay, so if something has a big resistance, for a given amount of potential difference, the current will be small. Okay, because if to make it big, I has to become small, right? You understand that? So the resistance is defined like that. So you take an element, you want to measure its resistance, apply a certain voltage, measure the current, and the voltage divided by current is it's called the resistance of that element. Okay, is that clear? Amina, R is equal to V over I, not I over V, okay?
Yeah, I realized
Okay,
that now.
all right, fine. So you can see that, right? You apply a certain voltage, say same voltage to two elements, and the one with a higher resistance will have a smaller current. The one with a smaller resistance will have a bigger current. So continuing on that, after we define the resistance, you can see since it is delta V over I, delta V has the unit V in SI units and I is ampere. So the unit for resistance is volt per ampere. As usual, since Ohm is the person who discovered this relationship between the define the resistance rather, it's not a define the resistance as the potential difference divided by the current. So the unit for resistance will be volt per ampere, but we say volt per ampere, we call it ohms. Again, because after him, he's the one who defined the resistance, so ohms. Well, this is actually not ohms, okay? This is omega, right? This is the big omega. It's a Greek letter, omega. But when we write it here, we say ohms. We don't say omega. Is that clear? This is the Greek letter omega. Well, there are two omegas in Greek. What's the difference between these two omegas? This is also omega. This is also omega. It's not W, this is Greek letter. This is the capital omega. This is the simple omega. Like in Roman alphabet, you have the capital A and small a. Like that in Greek, they have this capital omega, and this is the simple omega, lowercase, uppercase. Right? Are you all with me? So anyway, so why am I talking about that? Because that's the symbol. Ohms, V over A, we call it ohm, and the symbol for ohm is the letter omega. But we don't say omega, we call it ohms. Okay, right? Clear? The same function? No. This is for this is for frequency or angular frequency. We don't use this. For current, we use the capital omega. Okay. It's just a notation, a label. Okay. It's just a label. That's all. For force, actually kilogram meter per second square. This is what force is. But we are lazy to say kilogram meter per second square. So we have one single notation, N, Newton. Okay. So we are going to call it Newton, and the letter that represents Newton is big N. Like that, for resistance, which is volt per amperes, we just use the one thing called ohms, and the letter that represents ohm is the Greek letter omega. Is that clear, everyone? Okay.
Yes, Dr. Clear.
All right. Thank you, Amina. Ohm's law. So that what he defined, okay, when he defined the R, the resistance as potential difference divided by I is actually the definition of the resistance. But however, for some material, we call conductors in general, we know this delta V is proportional to the current. So that means R is a constant. The resistance is a constant. For some material, the resistance is a constant, meaning as we increase the voltage, the potential difference, the current will increase linearly, straight line relationship. That means the resistance is a constant. So that's why it was called Ohm's law, but actually the definition of the resistance, Ohm's law is not a law in the sense it is not applied universally. Only certain material, the resistance is a constant, then we can say it is a law, but it's a law, it's a misnomer. I mean, it's not correct to say it is law, but it applies to certain group of material conductors, many material. Experiments show that for many material, including most metals, the resistance remains constant over a wide range of applied voltage or current. So now this statement has become as Ohm's law. Ohm's law is an empirical relationship that is valid only for certain materials. So I should not call it Ohm's law, but anyway, the name states, so we have no choice. So actually, any material that obeys Ohm's law, we call it ohmic material. Right, now here we have a graph where the Ohm's law is obeyed because it's a graph of I against delta V. So we have a straight line. That means R is actually not the slope, 1 over slope, because I in the y-axis and delta V in the x-axis. So the relationship is delta V equal to IR. So delta V is the x-axis. So I should write I is equal to 1 over R delta V. I is the y-axis and delta V is the x-axis. The slope is 1 over R. Okay, got it? Because this is the y-axis here. That's how I have drawn. And delta V is the x-axis, so slope will be 1 over R. Slope is not equal to the resistance when you draw I versus delta V, but it is related to the resistance. It is 1 over resistance. But suppose you draw a graph of delta V in the y-axis and I in the x-axis, the slope is the resistance, provided it is a straight line. If it is not a straight line, what do we do? What happens? If not a straight line, the resistance is not constant. The way we define the resistance is delta V divided by delta V divided by I. 1 over resistance will be delta I divided by V. I divided by delta V. So this is a non-ohmic material because we don't have a straight line. So the resistance is not constant. The resistance changes. So here it will be one value for resistance. Here you'll have a different value for resistance, so on. So this is nonlinear. An example of material that show a relationship like this, a nonlinear relationship, is a diode. It's a non-ohmic device. Diode is a semiconductor. You don't have to know more details. Okay. So let's now, oops, did I miss some? Yeah, okay, I missed a slide. Okay. Resistivity. So we define resistance. Now we come to something called resistivity. Now what is resistivity? It is related to the resistance. The resistance of a ohmic, meaning something that obeys the Ohm's law. In other words, the resistance remain constant. For such material, ohmic conductors, the resistance is proportional to the length. So we take a piece of wire, say copper wire, and say with a fixed cross section, and another copper wire, double the length. If the resistance of this wire, say L, and this is length 2L, if the resistance of this is 10 ohms, say for example, this one will have a resistance of 20 ohm, because we have doubled the length and we said the resistance is proportional to the length. That means the resistance will also double when you double the length. So that's the meaning of proportionality, okay, linear proportion. So that's you understand. Also, we know the resistance is proportional to, inversely proportional to the area. That means, let me take two wires of the same length now. I am changing the length, but I am changing the cross-sectional area. This is a small area, and this is the big area. Now, what do you think will happen to the resistance? Because the current or the charges have more area
Will
to
be
flow.
smaller.
Yeah, it will become less, right? Because the current now can flow freely in a thick wire because it has more area to flow through, cross-sectional area to flow through. So it is understood the resistance should decrease in a thick wire. So that is why it is inversely proportional to the area. Now we combine these two, we can say resistance is proportional to L over A. And the proportionality constant is the resistivity. The proportion, it's a constant in the sense that it doesn't change. It is a constant for a given material. For copper, let's say copper is a given material. It has a certain resistivity. That resistivity for copper does not change when you change the length of the copper wire. Whether we have a short piece of copper wire or a long piece of copper wire, the resistivity is the same. Resistance will change, not the resistivity. Or whether we have a thin copper wire or a thick copper wire, doesn't matter. Resistivity will be the same. So the resistivity is a constant for a given material. Okay, so we call this is called the resistivity. This is the resistance, this is the resistivity. Here, the title of this, okay, resistivity. So you should know the difference now. Resistance for a given material can change depending on its length, its width, and so on. But the resistivity of a given material is a constant. And again, we have some symbols. R is for resistance, and this letter is again a Greek letter. It is not P. This is not P, okay? Anyone knows what is this Greek letter called? Michelle want me to repeat the resistivity. Michelle? I'm just looking at your chat, you know. Could you tell me which one? Yeah, okay, I will repeat. But let me, since I asked a question, I want an answer from someone. Okay, now, This is a Greek letter. This is for resistivity. What is the name of this Greek letter? It is not P. It's a Greek letter.
I don't know, maybe
You should know.
K?
No, it's rho, RHO, rho. Okay. It is also used for density, but here it is used for resistivity, rho, RHO. It's a Greek letter. So the Greek letter rho stands for resistivity. Okay. Let me repeat the whole thing again. Oops. Well, what's this capture? No, I don't want to capture. Not very clear. Okay. Okay. All right. So let me repeat the whole thing again. Resistance for, say, for a given copper wire, and we take two wires, one say 10 centimeter, the other one is 20 centimeter. Okay, with the same thickness. Okay, so we only change the length. We will see that if this has a resistance of 10 ohm, because I've doubled the length, the resistance will also double. So I say the resistance is proportional to the length. Mashal, are you with me? Is that clear? All right. So then we take, say again, the copper. I keep the same length, but keep the same length. I make the other one thicker, same length. This time I change the cross-sectional area, thicker. Then you find the resistance is inversely proportional to the cross-sectional area. So suppose the resistance here is a 10 ohms, and when I increase the thickness, double the thickness, let's say I make the thickness, maybe this is 1, now the thickness is 2, whatever the unit, then when you double the thickness, the resistance become halved. So that is what we call inversely proportional. So you got it? Very good. So we can combine these two together and we can say this is L over A. The constant of proportionality is called rho, and we call the rho is a property of a given material, constant for a given material. Say copper will have a certain resistivity, and aluminum, on the other hand, will have another resistivity. So it's a constant for a given material. Okay. So this is the equation that relate the resistance to resistivity. So we have a question. So let's do this question. Calculate the resistance per unit length of a 22 gauge. This is just the gauge give you the thickness, okay? Some notation, but we have the radius. So if it is another gauge, the radius will be different. Maybe it is in inches or something. Okay. So we don't care about this. We say there is a wire made of nichrome. Nichrome is a certain alloy. It's not an element, mixture of two metals probably. Okay, the nichrome wire has a radius of 0.321 millimeter. Yeah, what is here? And we are asked to find the resistance per unit length. How? Okay, we learned some formula here. The resistance is equal to resistivity length divided by area. We are asked to find the resistance, not really, we are asked to find the resistance per unit length. In other words, we are asked to find this. Do you understand that? Resistance per unit length mean R divided by L. So we don't care what the length is. We just want the resistance per unit length. In other words, we are asked to find R divided by L. I brought the L to this side, so we can say the resistance per unit length is equal to resistivity divided by area. So I can now solve the equation because the resistivity is given at the end. For the nichrome wire, this is the resistivity. It is given at the end of the question. So I can substitute that. Unit of the resistivity, I didn't talk about it. You'll find if you just, rho is equal to RA over L. If you substitute the unit, you can see the SI unit for resistivity will be ohm meter. Resistance unit is ohm, SI unit, but resistivity unit is ohm meter. So you substitute for resistivity and the area, okay? A wire, what kind of shape is a wire? Cross-sectional area of a wire is a circle, right? It's a cylinder. The cross-sectional area of a wire is a circle. Do you understand that?
I get it now.
You got it? Okay. Cross-section of a wire is a circle. Very good. So area of a circle is pi r squared, because this is cross-sectional area. So we know what pi is. You use the value from the calculator. Don't write 3.144 pi. You better make it accurate. So use the button from the calculator. It will give you more accurately with many significant digits. And for R, you substitute 0.321 millimeter. You better convert it into meter. How do you convert the millimeter into meter?
Divide by -3. Power of
Yeah, divide
-3.
by 1000. Yeah. So 10 to the minus 3 and whole thing squared, just substitute and get the answer. So B is done. A is done. B.
4.6 multiplied by 10 of
I
power.
don't know. Okay. Anyway, you just please check. Okay. I don't spare the, I'll leave it to you to get the answer. Okay. Let me, oops, where did I go? Okay. Let me clear everything here. Right. So we got A. Now what about B? If a potential difference of 10 volt is maintained across a 1 meter length of the nichrome wire, what is the current in the wire? So now we have found the resistance per unit length, which is whatever the value, let me call it X.
We multiply it, right?
Yeah, R will be 1 meter, right? Because we have now 1 meter wire. So multiply by 1 mean the same thing. The resistance will be whatever value you found in A, let me call it X, whatever that value. Then now he is asking, what is the current? So use the Ohm's law, because metals are ohmic devices, so you can use the Ohm's law. So I will be equal to V over R. V is 10 volt, and R, whatever you found from A, you substitute, you get the answer. Okay, then do the C also, but I'm not do it now. I want you to do it, okay? It's slightly, you need to use some common sense and see whether you can do it. Otherwise, I'll help you in the next class. I'll stop now. I have another class at 10:30. I need to let you go now. Any question? Is that good?
No, doctor, thank you.
You're welcome. See you. Assalamu alaikum.